I will begin with a word of prayer. Heavenly Father, we thank you for this day. Again, I thank you for this class and these students. Just ask you to guide our steps this morning, help us to glorify you what we do, and just to learn a little bit more about relations, Lord. And I pray, Lord Jesus. Amen. All right, so let me state the theorem we're working on today. And this theorem is, well, first of all, a lemma. First we do the lemma. Once we know the lemma, the theorem will be easy. So this is lemma. It's 5.2.13 in my notes as they're currently situated. And here it is. I'm going to change it just ever so slightly. Let S be a set. And R an equivalence relation. What's that mean? Means it's what? Symmetric?
Reflexive.
Yep, symmetric, reflexive. Yeah, reflexive, symmetric, and transitive. Very good. Equivalence relation on S. All right. If X and Y are elements of S, then we have a few things we can say. Part A, X is an element of the equivalence class containing X, which I guess the terminology kind of begs the question, doesn't it? I mean, I called it the equivalence class containing X. If that's what I'm calling it, it better be the case that X is an element of X, right? Otherwise, it's a really bad label, you know? But just because you call something doesn't make it so, right? So this is X is related to Y if and only if the equivalence class containing X is equal to the equivalence. I'll tell you what, instead of saying containing X, I'm going to say the equivalence class represented by X. Let me give us a careful definition of that. So at least I have some language which doesn't sort of assume the point here for the moment. All right, so X bracket, this is equal to Y in S such that X is related to Y. Oh, my bad. My squiggles are showing. Let's make this a R, X related to Y. So this is the equivalence class of R with representative X. Now, usually there's more than one choice of representative, all right? So that's something we have to keep in mind as we formulate arguments about equivalence classes. The fact that there's more than one representative, it becomes a point of contention for us at times. Okay, so X related to Y if and only if the equivalence class represented by X is equal to the equivalence class represented by Y. And then part C, and I think I have, so I don't know, what I have here is not, X is not related to Y. I've written like this, but let me just say that there's another notation for this, which is more common, which is like X/Y like that. X is not related to Y. We could use that notation. I think when I was typing up the notes, I couldn't find it in tech yet. I mean, I think this could be achieved in tech, an R with a slash through it. I just haven't figured it out yet. Anyway, so this, if and only if the equivalence class represented by X intersected with the equivalence class represented by Y is empty. Now, in the notes, I have I say that the equivalence class represented by X and the equivalence class represented by Y are disjoint. That's what that means, disjoint, right? Disjoint means that the intersection of the two sets is the empty set. All right. Now, I have to be careful not to prove C, because that is one of your homework problems. So I need to leave you guys, homework should be done at home. This is not your home, right? Is this your home? No. We used to joke when I was an undergraduate that we should bring like easy chairs to this one class because we had like so many So many classes in that particular classroom. We were like, we should have our own like recliner, so we can like just come and, you know, so people know this is our house. But I'm pretty sure if I brought a recliner there, it would have got stolen. It was NC State, so, you know. Anyway, although it was the late 90s, maybe it'd been fine. I don't know. Okay, so you guys help me out here. How's the proof of this look like? For A, observe if X is an element of S, then X is related to X by reflexive, right? I guess we could say by reflexivity. All right, there's a word for you. And then what? Thus what? X is an element of this by definition, right? Because what does it take for a point to be in the equivalence class represented by X? It must be related to X. X is related to X, therefore X is an element. So hooray, our terminology, the equivalence class containing X, is not a bad terminology actually, right? It actually is true. Okay. Then for part B here, this is an if and only if proof, right? So how should we do this? We'll assume that X and Y are in S and X is related to Y, right? Thus what? How about this? Y is, well, there's two different things to say here. All right, the one thing I can say is this shows you that Y, right, is an element of the equivalence class represented by X, right? By definition of equivalence class. Do you guys see that? See right here? But what else do we know? I guess I want to, let me try to, the trouble with this particular proof for me is there's like so many low-lying things I could say that they're just there to say, right? I could use symmetry. I could observe that by the same token, X is an element of the equivalence class represented by Y. Like we could say that, right? But let's pick something we're trying to prove. We're trying to prove this right here, right? But by the way, this is something I usually do when I'm proving things, is if I don't have, sometimes when I look about a proof, it's like the product of odd integers is odd, right? You look at that, you probably at this point know exactly what you're going to do, right? Like that doesn't require nuance and strategy. You just kind of write it down at some point once you've done enough of those. Something like this, something where you don't have a clear path to the end, sometimes what I do personally is I just start by writing down what the assumptions are, and then I write the next thing which is obvious from those assumptions. More often than not, that will lead me to the next step in the proof, even if I haven't thought of it before I write those words down. That's how I do. Now, sometimes that leads to sloppy proofs, and you need to like rewrite them afterwards. You know, I guess I could look at my notes, but I'm trying not to at the moment. So we're trying to prove this, right? So what I want to do first is I want to prove that the equivalence class containing X is a subset of the equivalence class containing Y, right? That's my goal. If I can show that, then that's half of it, right? Because then by double containment, we can get equality of the sets. So, all right, have I even started down the right path? I have Y is an element. Looks to me like looks to me like I'm on the way to looking at maybe this being a subset of that, you know? It looks to me like I'm working on that, and that's fine. We can do that just the same. right, so y is an element of the equivalence class containing x. All right, so if I want to show, excuse me guys, if I want to show that this is a subset of that, what should I do? I should say let, forget this also over here. That was a mistake. So let z be an element of the equivalence class containing y. All right? Then, by definition, that means what? Y is related to z, right? However, what else do we know? We know that y is related to x, right? By symmetry. See that? By the symmetric property, because we already knew x is related to y, so it follows that y is related to x, because we're working on an equivalence relation. What'd I do? I see a confusion. Oh, I'm sorry. I feel your pain. I'll try to write bigger. Or maybe a different color. This color is evil. But okay, so then what? We have y is related to z, and so we can reformulate this. So hence, again using symmetry, we have z is related to y, and y is related to x, right? Thus what? Yeah, z is related to x by what?
Oh, transitivity.
By transitivity, right? But what does this show? Hence, z is an element of the equivalence class represented by x, right? Because what does it take to gain entry into the equivalence class represented by x? You must be equivalent to x. But we have that z is equivalent to x now, right? What does this mean? This means that we've taken arbitrary point. We took an arbitrary point in the equivalence class represented by y, and we showed that that point is also in the equivalence class represented by x. That tells us, by definition of subset, that the equivalence class containing y is a subset of the equivalence class containing x. And at this point, we could replicate this argument, switching the roles of x and y, and make the same argument, right? Because x and y appear symmetrically in this discussion, in part because of the symmetry of the equivalence relation, right? So I will just say likewise, by a similar argument, the equivalence class containing x is a subset of the equivalence class containing y. Therefore, the equivalence class containing x is equal to the equivalence class containing y by double containment, right? Are we done proving B? Well, we're not done, right? At this point, all we've done, right? I try to put, I'm slipping up here, guys. I try to put this because I'm working on this direction of the proof. I'm working on the forward direction of the implication in part B. We still need to work on the reverse implication, right? So let's work on that next. I bet this part's going to be easier. So we're going to do what this time? We assume that the equivalence class containing x is equal to the equivalence class containing y, right? Then x is an element of the equivalence class containing y, and y is an element of the equivalence class containing x by part A, right? And the definition of set equality, right? Two sets are equal only if they have the same elements, right? So x has to be in the y equivalence class, and y has to be in the x equivalence class by part A. And but then what? You know, x is related to y, and y is related. Of course, we didn't need both of these, right? This is, you could cross out half of what I just wrote, right? We only needed to prove x is related to y, right? So, like if you'd like me to give you a more minimal proof, I could say, then x is an element of this, cross this out, you know, by part A, thus, there's a slightly, I'll put my proof on a diet. There you go. Wouldn't that be an evil kind of homework format? Proof diet. Remove unnecessary sentences in said proof. That sounds kind of evil. My wife dropped a class once because of that. She was taking this, well, starting to take this graduate course in statistical mechanics. And the first homework assignment was like, here's 70 pages of like papers. Find the errors. And she's like, I don't have time for this. I have to drop. All right, so there you go. That's part A. That's part B. Part C, we want to prove that, you know, two equivalence relations, two equivalence classes, two equivalence classes being disjoint is true if and only if x is not related to y, right? So part of the proof for part C probably should involve something like, if I pick a z which is in the intersection, right? If you think about it, if I picked z which was in the intersection of these two guys, then that would mean what? That would mean that z is related to x and z is related to y, hence by transitivity,
X is related to Y.
x is related to y, which then means that they're actually the same equivalence class, which then, of course, implies that. Anyway, I'm not giving you the answer to your homework problem. I'm just giving you just a little comment about these are the kinds of things you should be thinking about for that homework problem, right? So I'll leave part C to you guys. And if you get stuck on it, you can come talk to me about it. It's cool. All right, so that's it. Now the next theorem. So C is left to reader. And here's the theorem. I should write down for us. Let S be a set and R an equivalence relation on S, oh, no period here, then S mod R, or S divided by R, which, by the way, I'll remind you what that is, because that is the equivalence, the R equivalence classes, right? It's the set of equivalence classes of R, right? So this is just the definition. Here's the statement here. Forms a partition. What was a partition? Remember, it's a family of subsets of S whose union covers the whole set, right? And any two are disjoint unless they're the same one, right? And also every subset in the family has to be non-empty. So it's a collection of non-empty subsets whose union covers the whole set, and yet the sets in this family are disjoint from each other. Moreover, but it goes both ways. if A is a partition of S, then there exists an equivalence relation whose classes, whose equivalence classes, missed a word there, whose equivalence classes are the sets in A. All right. And essentially, this theorem's almost immediate from the lemma, but let's work through the proof. All right. So, we'll let S be a set with equivalence relation R, right? If observe that X is an element of the representative, the equivalence class of X. Do you guys mind if I don't write sub R on all of these? Because it gets really old. I mean, I can do it if you want. I mean, the same criticism back here, right? Maybe I should have written sub R on all of them. If there's no danger for confusion, we can leave off the sub R. Okay, anyway, so observe that X is an element of that by A of the lemma, right? Hence, let's see here. What am I trying to prove? I'm trying to prove that the union, hence X is an element of the union over X and S of the equivalence class. This is a very silly union. See what I'm doing? I'm taking the union of all equivalence classes. Perhaps I should, I'm using X in two different ways here. Let me not do that. By part A of lemma, let's say, hence Y is an element of this for any Y in S, since Y is an element of Y, right? In other words, I can take the case X equals to Y, and it's clearly in that union, right? Okay, anyway, let me not belabor this point, but it's not particularly difficult. Furthermore, notice, so we claim that the A equals to S by R is a partition. So I've already given you evidence that the union of the elements and union of the sets in the partition gives you the whole set, right? Why are they non-empty? X is an element of the equivalence class containing X, which is, of course, then not empty for each equivalence class X in the alleged partition, right? So they're non-empty because X is always in the equivalence class represented by X, right? It's impossible to have an empty equivalence class, right? By our definitions. And then finally, what's the last thing? A partition needs to be a collection of non-empty sets whose union is everything. And what's the last sticking point here? If x intersect y how can I say this? If x is not equal to y, then x intersect y is the empty set by C of the lemma, also known as your homework. Right, because if there was a commonality, if there was a point which was common to both of them, what ends up happening? Like we talked about, if there was a point in common to both of them, z, let's say, then x would be related to z, y would be related to z. Consequently, x would be related to y, but if x is related to y, then the equivalence class containing x and the equivalence class containing y is equal, right? So if we assume that the equivalence class represented by x and y are not equal, if they met at some point, that would then force equality, which gives us a contradiction, therefore they can't meet. I may be solving your homework problem, I'm sorry, but yes.
Are quotient set and partition interchangeable?
Yeah, well, no. A partition specifically is talking about, I mean, according to this theorem, yes, but logically, no. Logically, a partition is a collection of subsets of a set where each one of the subsets is non-empty. The union of all the subsets gives you the whole set, and the intersection of any two distinct ones must be empty. All right, so like that's a partition. Equivalence, the set of equivalence classes, S mod R or S quotient R, as you've rightly said, this is the collection of equivalence classes. That's a separate idea, right? Equivalence class containing X is by definition over there, you know, it's Y and S such that X is related to Y. On the surface of things, those don't look like the same idea, right? I don't think they do. So that's why this theorem is very powerful, is because it's connecting two very different ideas. Yeah. So at the moment, we've just proved what? We've proved that the we just proved that the set of equivalence classes partitions the set, right? In some sense, that's the first sentence here, right? What's the second sentence say? Moreover, if you have a partition, then there exists an equivalence relation whose equivalence classes are the sets in the partition. So we still haven't proved that. Let's do that now. And you guys, we're going to have to create. So let A form a partition of S. All right? Let X and Y be elements of S. Then we say X is related to Y if and only if what? What do you guys think? How should we define this equivalence relation? I mean, all I have to work with, right, is that we have a partition. How should I define, do you guys think? When would it be that X is related to Y? How about this? X and Y have to be elements of what? A particular subset that's in the partition, right? So if and only if there exists U in A for which X and Y are elements of U. Now, what we have to do is we have to prove that this definition for R is reflexive, symmetric, and transitive. If we do that, then we have constructed an equivalence relation, right, whose equivalence classes are clearly the partition which is given, right? This would make the given subsets in the partition, like if you think about what is the equivalence class for this definition, I can write it out over here, right? So, and maybe I should use something other than R here, like Let me use a t just for the sake of, I'm not talking about the r which was given in the first sentence, right guys? So let me use a t just to try to, separate myself logically from the first sentence. So observe the equivalence class of x with respect to t. Supposing this is an equivalence relation, just for the sake of discussion here to get us started, what would this be? This would be y in S such that what? X is t related to y, but what does that mean according to our definition just given? There exists what? There exists u in the given partition such that what? X and y are elements of u, right? It's not too hard to see that that is exactly the subset u. Whatever that u was. This is just u. For this particular, let me call it u naught. I put a naught on things when I'm thinking about them as being a fixed but arbitrary thing. It's just a thing I do. All right, so why is this t relation reflexive? T is reflexive, why? Since x is an element of u for some u in A for each x in S, right? Which means that, translating through our definition, that x is t related to x for all x in S. How do I know that there is a u in the partition where x is in? What did we assume? It's a partition, right? So that means the union of all these sets, all these u's, forms the whole set S. So therefore, that's why I know that. How about symmetric? This one's kind of dumb, right? If x is t related to y, then x and y are elements of u for some u in A, right? Thus what? This is really dumb. If x and y is an element of u, then y and x is also an element of u, right? Hence, y is t related to x. I find a lot of times, guys, that proving symmetry almost feels like you're doing nothing because we're so sloppy in our usual language in terms of keeping track of which came first and which came second, right? We abuse this commutativity of the and throughout our language without even thinking about it, right? You're like, well, isn't this, isn't this and that the same thing? Yes, they absolutely are, and that's why this relation, this t relation, is symmetric. And then transitive is a little bit more interesting. If we have x t relates to y and y t relates to z, then there exists, let's say, u1 and u2 in A such that what? X and y are elements of u1, and x and y and z are elements of u2, right? Thus what? What can you tell me about y? Y is an element of what? That was a 2. Thus y is an element of u1 intersect u2, right? Which apparently is not equal to the empty set because it's got an element in it, right? Just takes 1 point to not be the empty set. So what does this mean, though? We assume that A is a partition. Yeah.
U1 equals U2?
Right. So thus, U1 is equal to U2. And so, X and x and z are both elements of U1. Consequently, what? X is t related to z, all right? So I've showed that this t relation that we invented whole cloth from the concept of membership in the subsets forming the partition is in fact an equivalence relation, right? And this is the theorem. The theorem, again, just to put it in words, says to every partition there corresponds an equivalence relation, and to every equivalence relation there corresponds a partition. They're the same idea trapped in different, well, with different trappings, I suppose, but like these are equivalent ideas. All right? So. I know this theorem takes a while to say carefully, but this absolutely must be said in this class, because there's never a class after this where there's time to properly state this theorem and prove it. And yet, this theorem is the backdrop for many other theorems as you go on in mathematics, all right? Like, this is at the base of so many other things we do. Which I can't tell you about entirely, right? Because you haven't had those courses yet, which is kind of the awkwardness of this course in a nutshell, right? It's like we need more things to prove. All right. Let me erase this. There are stupid applications of this theorem that we just found, and one of the probably stupidest applications is the singleton partition. Right? Check this out. If we take any set, right? I guess this is example 1, huh? Let S be a set, non-empty, of course. Then let A be the following collection of subsets. X, such that X is an element of S, right? This is a partition. This is the singleton partition. It's a very dumb partition, right? I mean, I think it's dumb. All you're doing is taking every point in your set and saying, well, I'll just make this set containing just that point, right? Is the union of such things, again, S? Yeah, the union of all these gives you back S again. Is there intersection? How about definitely they only intersect if it's the same, the same subset, right? The only way they can intersect is if we're talking about the same point, same singleton. And yeah, I mean, this is a partition. What's the corresponding equivalence relation here? What are we saying? X is related to Y if and only if what? What's the equivalence relation here? It's very silly. Yep.
If x equals x.
If x.
If x equals y.
If x equals to y, right? So the equality is an equivalence relation, right? And the partition to which it corresponds is this exceedingly silly, partition, all right? Here's another one. And I don't think I put this one in the notes, and I'm not sure why, which makes me a little bit worried about telling it to you now. There must be a reason I put it in the notes. Maybe I'm about to find out why that is. Because I've forgotten why it is I didn't put it in the notes, because I always give this example. If we let S be set of smooth functions on R. So what are smooth functions on R? Now, we'll talk more carefully about what a function is eventually, but you guys already know, right? You get an input, you get a single output. Smooth, this word smooth means that you can take infinitely many derivatives. Right? You can take the derivative of one of these functions as many times as you like. All right? I've taken 10 derivatives. Can I take another one? The answer is yes. Yes, you can. I've taken 1,000,000 derivatives. Can you take another derivative? The answer, yes. Yes, you can. They're smooth functions. So we could do this. We could say like f and g and s has f equivalent to g if and only if f prime equals to g prime. Right? And by that I simply mean, by the way, guys, that f prime of x is equal to g prime of x for all x in R, right? I could say two functions are equivalent if and only if they have the same derivative. What's the equivalence classes in this case for this equivalence relation? What would the equivalence class, for example, of, let me make it more specific. I'll use the formula for the function if you'll forgive me for this, what's the word? It's sort of tasteless. It's like picking your nose at a party, mathematically speaking, something like that, I don't know. So x squared, like what's the equivalence class containing x squared? How about this? Anything of the form x squared plus a constant, right? Such that c is a real number, right? Anything of that form, if I differentiate it, what do I get? I get 2x, right? Derivative of x squared, 2x, right? So this is this is every kind of function that's equivalent to x squared under this equivalence, that they have the same derivative. So if I took an arbitrary function here, like, say, big F, and I asked what's the equivalence class of that, it would be like, big F plus a constant, where c is a real number, right? Have you ever worked with this equivalence relation before? What if, did you ever have like the integral of, 2x dx? What did you write? You wrote x squared plus a constant, didn't you? Why did you do that? Why did you write that plus a constant there? It's because you're not actually working with functions. Truth be told, you're working with an equivalence class of functions, where the equivalence is measured by whether or not those two allegedly equivalent things have the same derivative. Two antiderivatives are equally valid for a given integration if, when you differentiate those antiderivatives, you get the same integrand, right? Truthfully, if we were more honest, we wouldn't have students write this. We would have students write this. Because really, the indefinite integral is not a function, it's an equivalence class with respect to this equivalence relation. There's an example where equivalence classes were used in a previous class and you didn't even realize it. Unless you took my Calculus 1, in which case I mentioned this in passing because I'm just stupid. I don't know who I'm talking to, but I do say those things. I'm talking to a 5 sigma event is what I'm talking to, I guess. And if you know what that means, what's a 5? Who knows what a 5 sigma event is? All right. In physics, this terminology is common. You do experiments, right? And you test the likelihood of a result in terms of random chance, in terms of statistics. Usually there's some sort of Gaussian statistics going on. And so, like, in Gaussian statistics, the probability distribution has 70% of the stuff going on within plus or minus a sigma. That's the standard deviation. 86% of stuff happens within plus or minus 2 sigmas. 95% of stuff happens within plus or minus 3 sigmas, maybe more than that. By the time you get to 5 standard deviations, you have got the lion's share of all probable events in your distribution. So if you have, a 5 sigma event, that means that the likelihood of that experiment happening with respect to just random chance is pretty much nil. about every 5 years or so, there's some kind of major physics discovery that's achieved, quote unquote, discovery, which is achieved as a 3 sigma event, which can't be replicated, which then proves that, in fact, it's just random. It's noise that we're looking at. But, you know, if it's sufficiently spectacular, science news people will run with it. Anyway, I digress. I have a couple of other examples of equivalence relation in the notes, which I'm going to just sketch here very quickly without going through the details properly, if you guys don't mind. Another neat example of equivalence relation is if you have some space like this. Suppose your space has pieces. All right. You can define equivalence, an equivalence relation which is based on whether or not you can connect 2 points by a path. So like this point and this point, say P1 and P2, if you can connect them by a path. And so how to make that rigorous is this. You've got a function phi, which is a mapping from 0 to 1 to the space. All right. Such that phi of 0 is equal to P1 and phi of 1 is equal to P2. That's a path that goes from P1 to P2. All right. So you can say P1 is equivalent to P2, you know, if there is phi from P1 to P2 such that phi of 0, 1 is a subset of S. Now, at this point, I'm getting ahead of this game. I'm using stuff in the later part of this course that we haven't gotten to yet, so my apologies. All right. But what I'm saying is that all of the points on the path are within the space. All right. So because this path, this part right here, I could connect, you know, any of these other points, right? I can connect all these points, right? But in contrast, there's no way I could say connect P1 down here to say P3, right? This is outside the set. So this is called path equivalence. Two points in a set are equivalent if they're connected by a path. And if we take the set, and let me use squiggle for the equivalence. So here P1 equivalent to P2. So if I take S mod this equivalence, what does it give me? For my hypothetical example, it gives me what? How many equivalence classes? If you understand my very sketchy picture. So every point here is connected to every point here, right? All these points are connected together. Yeah. Just 4 classes, right. And those 4 classes are what are called the path components of the space. All right. So in this case, the equivalence, the set of equivalence classes tells us something about how the space can be parsed up into connected pieces. Right. This is something you would consider in topology. All right. This is a topological example. Another example, and this is a little bit even weirder. If we had some like space, for example, like this space, I'll call it M, and if I take a point P here in my space, so this could be like a sphere, cylinder, something more abstract than that, perhaps. And if you just look at curves that go through P, all right. If we look at a curve that goes through P, so this is a curve gamma, which is on M. I can look at the tangent vector to gamma, and I can visualize it like this. This is gamma prime of 0, all right? Let me maybe call this gamma 1, right? I can actually look at all possible paths that go through that point, all right? Like here's another one. And even though that goes, it's a different path, but the way it hits the point, it's still got the same, same velocity vector, gamma 2 prime of 0 is equal to gamma 1 prime of 0, all right? And I could say that gamma 1 is equivalent to gamma 2 in the sense that they're both paths which go through the point P, and they have the same velocity vector in that sense, right? And then, that is in fact an equivalence relation. And if we look at the equivalence class containing 1, what this is basically is a way of looking at the tangent vector at P. We can view the tangent vector at a point as being in one-to-one correspondence with an equivalence class of curves where they have matching derivatives at the point. This is a kind of more bizarre example, but I don't test on this because it really requires calculus 3 to properly, get into. All right, so that brings us to the last snippet here of my relations chapter, which I should share with you. I'm going to foolishly now attempt to use the projector. Anyone's guess what's about to happen? All right. I'm not getting excited yet. Fool me once, you know the rest. I think it's going to work. I think we're going to be all right. So there are other kinds of relations other than equivalence relations, right? To my taste, and the reason I have spent the lion's share of our time on equivalence relations is I think that they're the most interesting, and I also think they're probably the more easy thing to understand in the larger world of this discussion. But there are two, maybe three other important ideas we should talk about, and I think I gave you some homework about the other stuff. Let's see if I did or not. I don't know. If I can find my notes, that'd be great. You guys looking forward to break? You're like, no, I'm not going to know what to do without this class for like the next week. Could you please make some videos that I can watch over break? That would be great. I'm not going to do it. Wouldn't be prudent. That was a reference to a failed president. Never mind. But what am I talking about? The greatest presidents. Okay, where was I? So here we have equivalence relations. So some examples that I was just blathering about. There's more details there. Order relations. All right, come back to that in just a second here. Here's your homework. The next homework, right? Let's look at this for just a second. So for problem 51, problem 51 is just, so there's just a couple of induction examples. Right? These are just leftover induction problems. If you didn't get a chance to do the last induction homework for whatever reason, there's still a chance for you to achieve more induction, to take the next step, you could say. Of course, I won't say that because that would be a horrible pun. I guess I said it, so sorry. So this problem 51 is actually very interesting. It's one of the more interesting problems I've given you. I don't think it's that hard, but it might be unfamiliar territory, all right? So if you get stuck or something there, just come talk to me. Now, problem 53, I think you guys can be fine with that one. That one's not a big deal. Problem 54, we kind of talked about that stuff two classes ago. Problem 55, it is in fact an equivalence relation. All right, I'll tell you that. So you need to figure out why that is, but yeah, it is. Problem 56 is the thing I need to be careful not to finish proving today. Problem 57 is kind of a slightly souped up version of my example 2, right? It's a souped up version of my example 2. Find all equivalence relations on the set 1, 2, 3, 4. That would have been a very scary question before we had the theorem we have today, right? But with the theorem we have today, that's equivalent to the question of find all possible partitions of the set 1, 2, 3, 4, right? So, yeah. I'm not sure how many there are. I don't want to think about that much at the moment. Problem 59, I think that's rational numbers pretty much. And then problem 60 is well, it is what it is. I'm not going to say about that. All right, great. So so I guess if I have problems about order relations, they must be in the next homework. Yeah? If I forgot to give you guys homework on order relations, my apologies. Uh-oh. As Dr. Sprano says, we all make choices. Let's see here. It's fine. I'm not a petty person. I wouldn't take revenge. What's his name? No. I'm just kidding. I'm just kidding. So a relation is antisymmetric if and only if whenever x is related to y and y is related to x, then x is equal to y. This is quote-unquote antisymmetric. A partial ordering is a relation which is reflexive, antisymmetric, and transitive. A total ordering is a partial ordering in which x is related to y or y is related to x holds for every x and y in the domain of R. We likewise say that R is a partial or total ordering on the domain of R. Sometimes total orderings are also called simple orderings or linear orderings. So basically, a simple ordering or linear ordering is modeled over the idea of less than or equal to. All right? Think about this. If x is less than or equal to y, or y is less than or equal to x, that forces what? Forces x equals to y, right? So that's what a linear ordering is. And so this example right here just points out that if we sort through less than or equals to, it is in fact antisymmetric, because if we have x less than or equal to y and y is less than or equal to x, that forces x equal to y. And it's also transitive, of course, because if x is less than or equal to y and y is less than or equal to z, then x is less than or equal to z, so it's transitive. But it's not symmetric, is it? So this is not an equivalence relation, you know? It's got something in common, right? In fact, it's reflexive, right? X is less than or equal to x. That's true for any x. So it's reflexive. It's transitive, but it's certainly not symmetric. So less than or equals to is a so-called simple ordering, or if you like, a total ordering. Now, oh, there's a link. There's a link here. I discovered this thing teaching linear last semester, and this is one of the weirder things I've ever come across, but there's this movie called Zorn's Lemma, and I don't know, like, it's out there. It's really out there. And you can find these pretentious interviews with the guy who made it, with like various, cinema journalists or whatever. It is something to behold. But Zorn's lemma is actually a technical result in mathematics, which states that every partially ordered set in which every chain is bounded contains at least one maximal element. So here, a chain means a subset which is totally ordered. All right. So for that subset, you have a total ordering. There are two places I use Zorn's lemma in undergraduate mathematics, and any place you need to use Zorn's lemma in undergraduate mathematics, we're talking about a technical and foundational result. All right, like if you need to use that, it's something big. Anyway, so this example here is a nice example of an ordering which is not. Maybe you've had this feeling as you've worked on problems with subsets that it's like inequality. I mean, partly the notation makes you think it, right? But there is more to that, right? If we let x be a set and p be the power set of x, if we have u and v in the power set, then we can say that u is related to v if and only if u is a subset of v, right? That can be our definition. of this relation. All right?